Welcome to all of you. Today we discuss Michaelis-Menten equation for one substrate enzyme catalyzed reaction. Derive Michaelis-Menten equation for one substrate enzyme catalyzed reaction. V equals to V max concentration of S whole divided by Km plus concentration of S. Symbols having their usual meanings. And draw Michaelis-Menten saturation curve. One of the most basic enzymatic reactions first proposed by Michaelis-Menten 1913 involves a substrate S reacting with an enzyme E to form an enzyme substrate complex ES, which in turn is converted into a product P and the enzyme E. Schematically, we write S plus E substrate plus enzyme equals to ES is the enzyme substrate complex ES, and double-sided reaction. This K1 is this reaction constant rate, and inversely when ES convert to S plus E is K minus 1, K suffix minus 1, and ES to E plus P, enzyme plus product P, and K2 is the constant parameter. This is the only one-sided equation. Now, the law of mass action states that the rate of reaction is proportional to the product of the concentration of the reactants. And using this law, we get the nonlinear reaction equation, a system of nonlinear reaction equation. ddt of concentration S, third bracket in S means the concentration of S, rate of concentration S, this equals to minus K1 concentration of E into concentration of S plus K suffix minus 1 concentration of complex ES. Because first equation of 2, the rate of change of concentration S, this is the rate of change of concentration S, is made up of the loss rate to E and S. So this is minus K1, loss of E and S. The rate of concentration of S equals to the loss of the concentration, loss rate of E, concentration of E and concentration of S. So it is minus. And also gain rate proportional to complex ES. So this is the minus K. In this direction is the minus suffix K. So plus K suffix minus 1 concentration of the complex ES. So ddt of concentration of S equals to minus K1 is the loss rate, because this S is loss rate in this direction, and this is the gain rate in this direction, left-handed direction, and loss rate is the right-handed direction for S. And similarly, for the rate of change of the concentration E, so this is the loss rate of the complex ES, E into S, E and S. So minus K1 concentration of E, concentration of S plus, and this is the E. So K minus 1, K minus 1 in this direction. So complex concentration of the complex ES, this is into K minus 1, K sub x minus 1, and also this is the gain rate of this E, and this gain rate also E, here is E, so gain rate K2 into concentration of ES, and the uh, rate of change of the concentration of ES, that is derivative of concentration of ES, equals to K1 into this. So this we get by gain rate of S, concentration of S and concentration of E. So K1 into concentration of E and concentration of S minus because is the loss rate this. So this minus K suffix minus 1 E concentration of ES, and this is the K minus K2 concentration of ES. And lastly, for the product P, the rate of change of the concentration of P, that is derivative of concentration of P, equals to this is the gain rate of the concentration of the constant ES. So we get the last equation, derivative of concentration of P equal to K2 concentration of ES, where third brackets denotes the concentration of the reactant. Now we assume here during the reaction of concentration of enzyme substrate complex ES remains constant. So derivative of concentration of ES equals to 0 and is lower than the concentration of unbound substrate concentration S, which is lower. And these assumptions are known as a steady state approximation. This is the steady state approximation. By this approximation, by this assumption, we have derivative of concentration of ES equals to 0. So from the third equation of the system 2, derivative of ES equals to 0. So obviously K1 concentration of E into concentration of S equal to K minus 1 plus K2 concentration of ES. And in order to determine the rate of product formation means this is the P. Rate of product formation is this. So rate of product formation derivative of the concentration of P is equal to V. This is the velocity of this reaction. Equal to derivative of P, obviously this is equal to K2 into concentration of complex ES by the last equation of the fourth equation of the system 2. Now the total enzyme concentration ET is given by ET equals to concentration of ET equals to concentration of E plus concentration of complex ES. Now we help this graph. This is the horizontal axis, is the time axis, and vertical axis is the concentration axis. So at time initially the concentration of the enzyme, this E0, this is the point E0, and when the reaction progresses, this is the concentration downwards. This is the concentration of E downwards. So and this ES is the complex. Initially, this is the concentration of the complex ES is 0. And there's red curve, this, and during when the reaction is going on, then the concentration of ES is almost constant. So derivative of ES by dt equals to approximately 0. And this E0, actually this E0 is the total concentration. ES, concentration of ES plus concentration of E. So if we draw a horizontal line, this parallel to the time axis, this horizontal line gives the total concentration of ET, concentration ET. This is the concentration of ES, complex ES plus concentration of E. And initially, the substrate product is concentration is P0 initially at this point, and the substrate is equals to initially S0. And during the process, this concentration of S along this green curve downwards with time. Time t increases, then the concentration of S substrate is downwards decreasing. And the product initially P0, concentration P0, during the reaction process, this concentration of the product P blue curve, this with time, this is the increases with time, and this is the thermodynamic equilibrium of this state. So this portion is the pre-steady state, and from this portion is the steady state. When the steady state, this is the thermodynamic equilibrium of this. So this is the graph of this. So concentration of E equals to concentration of ET minus concentration of ES. And using this value in 4, value of concentration of E, and put this value, and after simplification, and we get the concentration of the complex ES equals to K1 complex concentration of ET and into concentration of S by K suffix minus 1 plus K2 plus K1 into concentration of S. And this equals to dividing by K1, we get this. Now, this K suffix minus 1 plus K2 by K1 equal to Km. This Km, and this is the, now V is the velocity of reaction, this equal to K2 into ES, concentration of ES. This the V is the K2 into concentration of ES, equation 5. So concentration of ES equals to concentration of ET into concentration of S into Km plus concentration of S, where Km is called the Michaelis constant, which measures the substrate affinity for the enzyme. If Vmax is the reaction velocity at saturating substrate concentration, that is when ES equals to ET, that is Vmax is equal to K2 into ET. K2 into ET is the saturating the substrate concentration. So if we put K2 into ET equals to Vmax, Vmax is the reaction velocity when a substrate concentration is saturating. And this, from this graph, this is the substrate concentration, this, and this is the vertical axis is the reaction rate, this V. So when S is tends to infinity, when S tends to infinity, then V goes to Vmax. This is the Vmax is constant, and this is the initial value, this. So we get Vmax is equal to K2 into concentration of ET, and using 9 we get V is the Vmax into concentration of S divided by concentration of S plus Km, and this is known as the Michaelis-Menten equation for a one substrate enzyme catalyzed reaction. Now, if Km equals to the constant of S, numerically equal to constant of S, Km equal to constant of S, then put here Km equal to constant of S, then we get this Vmax by 2. So when Km equals to the concentration of S, then we get V is equal to Vmax by 2. And when concentration of S approaches infinity, then from equation 10, we get Vmax by 1 plus Km by concentration of S. So this S tends to infinity, concentration of S tends to infinity. So this equals to 0. So V equal to Vmax. So when concentration of S tends to infinity, then V equals to Vmax. And this from this figure, this graph for the equation 10, we get this Km, then Vmax is this is the constant at the high concentration of the substrate S. When K is this is the Km is the Vmax by 2 is Vmax, so Vmax by 2 is this, so Km is this. So Km is this when Vmax V is equal to Vmax by 2. When concentration of S is greater than Km, value of concentration of S is greater than greater than Km, then Vmax V is a constant value. The velocity of reaction is the zero order. This is the horizontal line, and this is the V is equal to Vmax is constant and is independent of the concentration of S. At the lower concentration of the substrate, that is when concentration of S is less than Km, the velocity of reaction is a first order equation, that is, and velocity of reaction is proportional to the substrate concentration S. And this curve is the Michaelis-Menten saturation curve. This, and from this graph we can determine the value of Km and Vmax. Note that from equation 10 we can easily write by reciprocal of this 1 by V is equals to concentration of S plus concentration S plus concentration of Km whole divided by Vmax in concentration of S. After simplification, we get this 1 by V equal to Km by Vmax into 1 by concentration of S plus 1 by Vmax. Comparing with this, y equal to mx plus c form. So y equal to 1 by V, x equals to 1 by concentration of S. So slope of this Km by Vmax. So if we draw this double reciprocal plot along the horizontal axis 1 by concentration of S and the vertical axis is the 1 by V velocity, then this graph, this is the slope of this Km by Vmax. And obviously, if we put 1 by S equals to 0 and then 1 by V equal to 1 by Vmax, so this point gives the value 1 by Vmax. And if we put 1 by V equal to 0, then 1 by concentration of S equals to minus 1 by Km, and this point and gives the minus 1 by Km. And this line has a slope of Km by Vmax, and the intercept of 1 by Vmax on the 1 by V axis, and an intercept of 1 by Km on the 1 by constant of S axis. And we can more accurately determine by the value of Vmax and Km more accurately by this graph. Thank you for watching this video.